Steve. So then, welcome everybody to the Physics Discussion Colloquium. This is the third edition of this colloquium. Professor Steve, it's a great honor to have you here. If you're watching in YouTube or here in Zoom, you can type your question. We're gonna read your question during the talk. So today, we're very happy to have Dr. Steve Strogatz here. He's a Jacob Gold Schurman Professor of Applied Mathematics at Cornell University. Steve is one of the great mass communicators of math in recent times. He is the author of several books, and he was a frequent contributor to the New York Times. His research work involves a large variety of applied mathematics, including mathematical biology and complex systems network theory. So she is also a specialist in nonlinear dynamics with several contributions to the study of synchronization in dynamical system. And that's exactly what he's going to talk today. So again, thanks, Steve. Welcome to the colloquium, and you can start your presentation.
All right, thank you very much, Egan, and welcome everybody. Very excited to be here in Brazil virtually. Hope to be there in real life soon. Okay, let me share my screen and let's try that. Okay, share screen. Good. All right, that is visible, I hope.
Yes.
Yes, good. All right, perfect. So my topic today is networks, and specifically networks of oscillators that manage to get themselves in sync. The work that I'll be describing is pretty recent. We just published it in the last year. Alex Townsend is one of my co-authors. He's a new youngish, you can see, sort of young assistant professor in math department at Cornell. And we also have Mike Stillman collaborating with us as well. So Alex is a specialist in numerical analysis, and Mike Stillman does algebraic geometry. And together, these things combined with the nonlinear dynamics that I tend to know about to show some interesting aspects of this problem that I want to describe. All right, so first, the phenomenon of synchronization. It's really all over the place in the natural world. You've probably heard of this phenomenon in Southeast Asia, in places like Thailand or Malaysia, where male fireflies will gather in the trees at night, specifically in mangrove trees along tidal rivers that run out to the sea. And these fireflies will congregate in the trees and then begin flashing in unison. So if you haven't seen it before, let me just show you a little clip here in the video, and watch carefully to see if you really think they're synchronized or not. When I look at this, I think I'm seeing waves propagating. You can see that there's very good coherence. I mean, a lot of the flashes are occurring nearly simultaneously, but it does look like there's a progression in phase. They're not exactly all in sync the way you might have naively thought. Still, it's a fantastic example of self-organization. How are these fireflies doing this? There's also a phenomenon where neurons will get synchronized. So in this demonstration on the upper right, what I'm going to show here is this is a petri dish with neurons that have been taken from a thalamus or a cortex of a mammalian brain. And they're allowed to creep around until they make connections with each other. And then they're treated with a calcium-sensitive dye, which has the effect that when they when they fire an action potential, you can actually see them as if they were fireflies flashing. That wouldn't normally be the case, but with this calcium-sensitive dye, you can actually watch the synchronization. So keep your eye on the neurons. Boom. You see a large number of them go off, boom, simultaneously. And it doesn't really look like waves in that case, at least not to me. And so, of course, synchronization is not just something that happens in a petri dish. We think it's an essential part of a lot of different brain functions, from attention to memory. And also it's involved in some pathological brain states like epilepsy. So there's a lot of reasons to be interested in synchronization. And what I want to discuss with you is that, like, the absolute simplest mathematical description of a synchronizing system of oscillators. So here's my image of an idealized oscillator. Just think of it as a point running around on a circle, or if you want, an arrow that goes around a circle. This circle represents the cycle of states in the state space of whatever the neuron or the firefly is when it executes its periodic behavior. Now I'm going to use colors. Like here you see red indicating this phase of 0. Let me let this go around. Here's the arrows moving around as the oscillator goes through its cycle of states. And notice that the colors are changing. So throughout this talk, I'm going to use color as an indicator of the phase of an oscillation in its cycle. Color has this very convenient topology that psychologically red is close to violet, so that the topology of colors is actually a circle in terms of our perception, right? I mean, even though frequencies go from red to violet, like a segment of the real line from low frequency to high frequency, perceptually we think of violet as near red. So it's as if the ends of the line segment have been joined to make a circle, which is good because the circle is the right topology we want for anything that's executing a periodic behavior in its state space. Okay, so anyway, here's a graph consisting of many oscillators where an edge between two of them means that they are influencing each other somehow. So coupling is indicated by a line connecting two dots. And you'll notice at the moment that they're started at random phases. There's all kinds of different colors. I'm going to let them evolve according to a certain differential equation that I'll describe in a minute. But what you should watch, and watch closely, is that the colors will quickly come into sync. They'll all start to be the same color. All right, ready? Watch. After just a few flashes, you see they're all going now with the same, they're all in phase. They're all showing the same color. So this system has spontaneously synchronized from a random initial condition. Now, the differential equation that was causing that to happen is this differential equation, which is what I'll be spending the rest of the talk on. It's the simplest possible model that I can think of anyway for a network of oscillators. So let's walk through it. Here's the phase, theta. That's that point on the circle. It moves around the circle at a rate d theta I by dt at some natural frequency omega. Notice that the omega doesn't have any subscript I on it. It's just the same omega for all oscillators. So in that sense, we're restricting to an extremely idealized case where the oscillators are perfectly identical in their frequency. People have looked at the case where the omegas are not identical, where they're, say, distributed according to some probability distribution. That, in fact, is what this gentleman, Yoshiki Kuramoto, a Japanese statistical physicist, did back in 1975 when he created essentially this equation that we've been studying now for more than 45 years. But Kuramoto allowed for non-identical frequencies, and he assumed a very particular coupling pattern, different from what I've shown here. He assumed that every oscillator is connected equally to every other. So in terms of graph theory, he was thinking about the complete graph, where every pair of oscillators is equally strongly interacting. So what he did was consider complications in the omega by making them non-identical, and simplifications in the topology by making everyone connected to everyone equally strongly. Today, I want to do the opposite sort of thing, where the omegas are all going to be the same, but I'm going to allow different network structure than just the complete graph. So the network structure will be defined by an adjacency matrix, which is filled with zeros and ones. Aij equals 0 means that I and j are not connected at all, whereas Aij equals 1 means that I and j are connected and they're interacting with a unit of coupling strength. So I'll assume that that is the same for either they're coupled or not, and the coupling strength will all be just 1. So it's as simple as can be. And the reason I'm doing all that is because I want to examine the interplay between the topology of the network, the graph structure built into this Aij, and its propensity to get in sync or not. That's the question. How does the structure of the network affect its ability to synchronize? One last thing, this sine function is the coupling function that tends to promote synchrony. And the way it works, you can think about it. I mean, imagine theta j is a little bit ahead of theta I on the circle. Like picture two runners running around a track. If one runner is a little bit ahead, then the angle difference between them, which would go in here, will be some small positive number. Take sine of that small positive number, it'll be positive. And then this is a 1 because those two are connected. So the point is that if j is a little bit ahead of I, it adds a positive contribution to omega, which makes I speed up. In other words, with two runners running around a track, the runner who's behind will tend to speed up, and the runner who is ahead will tend to slow down, and that tends to bring them into sync. So this is a synchronizing interaction. Nevertheless, because of the graph structure, it may not be sufficient to get the whole system in sync. So here are a few examples of different topologies. This is a random graph where every pair of oscillators is connected with probability 0.1. So in other words, you think of two oscillators, and with probability 0.1, you put an edge between them, and probability 0.9, they're not connected. And you do that for every pair, and you end up getting this random graph structure. And now, look, the oscillators are at random phases. I start the system, and let's see if it gets in sync. All right, so 1, 2, 3, go. You see it very rapidly got itself into sync. Now, you might wonder, does everything always synchronize? And the answer is no, some things don't. So here's an example where I have 44 oscillators arranged in a ring, but they're also connected not just to their nearest neighbors, but also to many second and third and fourth neighbors, and so on. That's why the picture looks so dense. It's not that everyone's connected to everyone, but everyone is connected to a certain number of oscillators on either side. Now, here initially, we have a full cycle of phase, and watch how that evolves in time. All right, watch. So you see the colors rotating around in a rotating wave. The same thing happens here on this cyclic graph where they're only connected to their nearest neighbors. And again, you see this rotating wave. What this should remind you of is the phenomenon at like a football game, a soccer game, where the fans will sometimes all stand up and then sit down, right? They sometimes call it the Mexican wave. It rotates around the stadium. This is not synchrony. This is a different kind of structure. As you can see, the colors are not all the same. So rotating waves can compete with synchrony, and that's one of the things I'll be interested in. Which types of graphs only have a synchronized state as their attractor, or do they allow for other possible attractors like these rotating waves, or even more exotic attractors? That's the question. So let me say that in a little more detail. The question I want to think about is the issue of global synchrony. And so I'll define a graph or a network to be globally synchronizing if in the long run, all the oscillators end up in phase. Now, there could be some exceptional initial conditions. Like you could have a certain number of oscillators at one phase and another set of oscillators exactly pi out of phase. You can set that up. That will satisfy the governing equations. So there could be some initial conditions that don't end up in sync. But if that exceptional set is of measure 0, then we would say that the system is globally synchronizing. It synchronizes for almost all initial conditions. All right, so like you could say it another way, with probability 1, it will synchronize. That's what we mean. All right, so the questions I want to look at then are, first of all, there's some competition between sparsity of the graph and density and its ability to synchronize. And so sparse graphs tend to not synchronize. We saw that in the previous example, that cyclic graph that only had nearest neighbor connections, that allowed for a rotating wave, a tractor. We could ask, what's the sparsest graph that doesn't have any of these rotating waves? What's the sparsest graph that is guaranteed to synchronize? Or you could go to the other end of the spectrum and ask, what is the densest graph that has other attractors besides synchrony? What's the densest graph that does not globally synchronize? And so this second question, I mean, it turns out the first question is kind of easy, and we'll dispense with it very quickly. The second question is hard, and we don't know the answer to it. This is a problem that people are working on very actively right now. So with my first grad student, Shinya Watanabe, we had some results a long time ago in 1994. There was a big breakthrough from Richard Taylor, an Australian mathematician, in 2012. And since then, there's been a lot of activity, but still no solution to this question. So I want to help you love this question and maybe even work on it. I think it's a really cool question. And so I'll try to explain why I like it so much. Okay. So first, let's take care of this easier question. What's the sparsest graph that is guaranteed to globally synchronize? Well, before we answer that, let's just do a little bit of simplification of the model. Here it is again. I can get rid of this omega without loss of generality. So how do we do that? Well, the same as you would in a physics course, you would go into a rotating frame that's rotating at the frequency omega. Just pick the right reference frame. So in other words, if I define a new variable, theta hat, to be the original thetas minus omega t, if you substitute that in here, here, and here, you'll end up creating an omega on this side of the equation that cancels this omega. And you're left with this system that looks the same as the original system, except it doesn't have any omega in it. So the theta hats you can interpret as the relative phases of the oscillators in this rotating frame. And so if you watch how the theta hats evolve over time, when a system synchronizes, they will do some complicated thing at first, but then they end up all being the same angle, differing only by 2 pi, but on the circle, that looks like the same angle. So this is what, then if I want to just show you again, what does it look like when a system self-synchronizes? There's an example with my graph, the random graph that gets into sync. But so this system with the theta I hats has the advantage that now, instead of looking for periodic solutions corresponding to these synchronized states or the waves, now we're just looking for equilibrium points. And that's very convenient because it's relatively easy to find equilibrium points, or fixed points as they're sometimes called. Even though this is a high-dimensional nonlinear dynamical system with a complicated topology, Aij, nevertheless, it has some very nice structure. In particular, it is, let's assume the Aij is symmetric. So if I is connected to j, that means j is connected to I. In other words, it's an undirected graph. If you have that symmetry, then the system can be written as a gradient system. It has a potential v given by this cosine expression, such that the gradient of this v, negative gradient, is the d theta hat dt. And so why gradient systems are so important is that they have really easy long-term dynamics. The only thing that can happen in a gradient system is that the trajectories flow downhill, going down the potential until they reach an equilibrium point, and that's it. It might be a sink, it might be a saddle point, but all that can happen in the long run is equilibrium. So what that means is there's no periodic solutions for the theta hats, there's no quasi-periodicity, there's certainly no chaos. All you have is equilibrium behavior in the long run. And that's because you can prove that the potential V just decreases monotonically on any trajectory until you end up at an equilibrium. So that's it. So we've reduced the problem, a dynamics problem, to a problem of studying equilibria, which is just an algebraic problem. We just are looking now for equilibrium points, that is, solutions of this d theta dt equals 0. And so we have to solve this big system of trigonometric equations for the thetas to find all possible equilibrium points. All right, now in general, that's not going to be possible. That's a really hard problem. In fact, even though it's not a differential equation, you can't really solve this. It's a big, nasty system in general when the Aij is some complicated network. But there are some special cases where we can make progress. So let's first, though, comment that if you did find an equilibrium point, you'd want to know, is it stable or not? And to determine the stability of the point, you calculate the linearization of this about the fixed point. So that gives you this so-called Jacobian matrix. And by looking at the eigenvalues of the Jacobian matrix, we can determine whether we have an attracting equilibrium point or one that's a saddle or a repulsive equilibrium point. Actually, maybe this is a good time to pause. I would like questions as I'm going. So does anyone want to bring up anything either in the chat, or you can unmute yourself and just ask something out loud? If you're on YouTube, so maybe you can send something and we can look in the chat.
There is a questions from YouTube. I type on the chat. Do you want me to read, or do you want to read?
I see the question.
Okay.
The question from Sarika says, when I say a set of measures 0, do I mean those having a rational initial frequency? It's not really what I meant. So when I speak of a set of measures 0, I'm talking about in the space of the thetas. We're not talking about the frequencies. So the thetas, remember, there's one theta for each oscillator. I have n oscillators. So I have an n-dimensional space. Think of it as, it's really like it's an n-dimensional torus, in fact. Or if you would rather, you could picture it as an n-dimensional cube that's solid, running from 0 to 2 pi on each axis, but with periodic boundary conditions on all the axes so that 0 and 2 pi are identified. Anyway, that's the n-dimensional torus. And what I mean about measure 0 is measure 0 as a set of initial conditions in that torus. Okay, another question. Hello, can we identify the rotating waves in random graphs with small p? Or does this feature have something to do with finite dimensionality? So if I understand the question, when you speak of a random graph with a small parameter p, that will be a relatively sparse random graph. And those would be the random graphs that would have the most chance intuitively of having rotating waves or other attractors besides the perfectly synchronized state. So yeah, I'm not really going to be talking too much about the rotating waves in the context of random graphs. I'll be spending most of the lecture talking about graphs that have a lot of symmetry where we can do the analysis in detail. There is interesting work about random graphs, but I won't have a chance to talk about it here. Let's see, Rasha asks, why is a Mexican wave not an example of synchronization? So I'm defining synchronization to mean all the phases the same. So it's the strongest possible kind of synchronization, meaning everyone is firing at the same time. In a Mexican wave, that would be an example of what I would call phase locking, or that is, the relative phases are staying constant, but they're not 0. So it's a frequency synchronization, but it's not a perfect in-phase synchronization. So that's the distinction that's being made. It's a kind of synchronization, but I'm talking here about the strictest kind where everyone is exactly in phase. Okay, so let me continue. Thanks for those great questions, everybody. All right. So here, onto the question of the sparsest graph that can get itself into sync. Suppose I have n vertices, and I want to add as few edges as possible to make the system synchronize with probability 1 in the sense I just described of everyone getting in phase. It turns out any tree will do that. That you can just start connecting a tree, the nodes in this way to make a tree, meaning no loops in the graph. It turns out that if you have a tree, you can prove that that synchronizes for all initial conditions except the set of measure 0. And the proof is not really that difficult. You can check that on a tree, if you pick one of the phases, say theta 1 hat, all the other phases have to differ from it when you solve those sign equilibrium equations. They have to either be the same phase as theta 1 hat or differing by pi. Those are the only equilibrium points. There's a very simple structure for the equilibrium. And then you can check that the ones that have any pi's in them, they're unstable. Because by doing this little linear algebra calculation I'm showing below, you can produce an eigenvalue greater than 0, which is what we want if we want to show that the state is unstable. Since I'm dealing with symmetric matrices here, all my eigenvalues will be real. So the test for stability is, are all the eigenvalues negative? If so, then I have a stable state. If I have any positive eigenvalues, it's unstable. So the answer is boring. A tree is the sparsest self-synchronizing system. Okay, now here's a little technical thing that I don't want to spend too much time on, but since I'm talking about trees, it's worth making this comment now, which is that if I have some graph and I want to know, is it globally synchronizing or not, there's a useful thing that I can sometimes do where I look at a bigger graph that is different by having one extra node, this one shown here, and one extra edge. So it's as if I've added a twig, that is an edge and one node, to a pre-existing graph. Or you could look at it the other way. I might have a graph like this with a twig, and I could consider chopping off this twig by chopping off this one node and this one edge, and now I have a smaller structure. So in that sense, I have pruned off a tree. I've cut off a twig. Rather than cutting off a twig, I could cut off a whole tree, but I'm just going to focus on cutting off one edge and one node. The reason I go into this is because we can prove that the stability properties of a graph like this and the graph I get by cutting off a twig, they have the same stability properties relative to global synchronization. In other words, we can prove that if this bigger system globally synchronizes, then so does the smaller system with the twig removed. Or if it doesn't globally synchronize, the same is true with the twig removed. So in other words, we can either add or delete trees as necessary when they are in this kind of configuration without changing stability properties. And so I'll make use of that later. There's an argument for it in terms of perturbing a Jacobian by a rank 1 perturbation, but I don't really need to go into that with you. Just take my word for it that this will be a useful reduction technique for us later. Okay, so now into the heart of the talk, which is how dense can a graph be and still have the property that it can have other attractors than pure synchrony? Are there any dense graphs that can support, say, Mexican waves or other interesting attractors? So here's what's known. There are relatively dense graphs that don't globally synchronize. It's something that I noticed with my students, Dan Wiley and Michelle Gervin, back in 2006. And actually, some great work has been done in South America by Canali and Monzon in 2015 on this topic. So here's an example of a pretty dense graph. This is it's like something we looked at earlier. You've got 32 oscillators. Each one has degree 20, which means in this case, each one is connected to 10 neighbors on either side of itself. And then that structure is repeated in a circularly symmetric way. Okay, so everybody is connected to their 10 nearest neighbors on either side in this ring geometry. It's pretty dense, as you can see, but if you let it run, you can see it will support this rotating wave. And that will continue forever. I mean, that state is stable. If perturbed, it'll come back to that. So you can have I'm going to use this kind of number as a measure of the density. the 64% is saying that each oscillator is connected to 64% of the rest of the system, and yet it still has other attractors than synchrony. Now, if a graph is sufficiently dense, people have been able to prove that it does globally synchronize. So here's an extreme case with my student Shinya Watanabe. We proved a long time ago that if the graph is fully connected, it's a complete graph, it will globally synchronize. With this, again, assuming this Kuramoto sign coupling. Here, this notation, delta G, means the degree, the degree of the node of minimum degree. So in other words, if each node is connected to all the others, in this case, the size of the graph, n minus 1, if that's the minimum of the degrees, well, in other words, if everyone's connected to everyone, that will globally synchronize. But the neat thing that was shown by Richard Taylor, that was, as I described earlier, a breakthrough in 2012, was noticing that he didn't need to have fully connected. If the graph only had 93% connectance, like in other words, if each node is connected to at least 93% of all the other nodes, and it doesn't matter which 93%, it doesn't have to be any geometrically regular thing. You could pick the 93% at random, whatever. If each node is connected to at least 93% of the others, he proved that that system would globally synchronize, which was really interesting, that just that number was enough to ensure global synchrony. He did that by some linear algebra calculations, showing that all the possible equilibrium states other than pure synchrony would be unstable. And so this is what people have been improving now recently. In 2018, Ling and collaborators showed that they could improve Taylor's 93% by a dramatic amount, down to 79%. If each node is connected to at least 79.29% of the others, the system will always end up in sync with probability 1. And then just recently, Liu and Steinerberger improved that number a little bit down to 78.89%. And so you can see that there's a kind of a quest here to find what is this number? Like, is there a magic number? Is there some critical number with the following property, that when this number is like, whatever this number is, there's say 75%. Could it be that 75% is the magic number such that when you're connected to more than 75% of the other nodes, that will guarantee synchrony? But if it's less than 75%, there will be some graph that can support another pattern besides global synchrony. What is that magic number? We don't know what it is. We know that an upper bound on it is 78%, 78.89%. But what's the best number? So that's the thing that we wanted to understand, Mike Stillman and Alex Townsend and I. And so, as I say, this is the state of the art, 78.89%. We also know from my old work with my students, Wiley and Gervin, that there's a lower bound on the magic number of 68%. Because we've constructed examples where each node is connected to 68% of the rest of the system that support Mexican waves. And so what I want you to notice is that 68 and 78 are not that far apart. There's the magic number, whatever it is somewhere between 68 and 78. But what is it? I don't know the answer. The answer is not known. So I hope that you'll find this question interesting. But I'll tell you what progress we've made on trying to find the number. Okay, so one thing to notice is that these graphs that my students and I considered, that now people are calling, named after us, the WSG graphs, Wiley, Strogatz, Gervin graphs. It's kind of ridiculous, actually, because they're just rings with non-nearest neighbor coupling. But okay, anyway, these graphs do support these Mexican wave states, which we sometimes call twisted states, because if you think about how the phase changes as you move around the ring, the phase is changing in a uniform way. It's like you've got a twisted ribbon going around the ring. So here, look at this structure. That's a graph with 8 vertices, each one connected to 4. So it has 57%. Each one's connected to 57% of the rest of the system. There's its little Mexican wave running around. Here's this much denser graph that we talked about earlier on the right. It too has a Mexican wave. We wanted to generalize from those examples to any kind of graph that has circular symmetry, so-called circulant graphs, to look for better bounds than what we had achieved. We wondered, could we do better than this 68% lower bound? And so to think about it, we set up the problem as a linear algebra problem, write the theta hats as a vector, use this notation for the cosines and sines of those numbers. And then this equilibrium equation that we wrote earlier converts to this little matrix equation, where the A is the adjacency matrix that we talked about earlier, and the D's are the diagonal matrices of the cosines and the sines. And so we are interested in understanding the eigenvalues of the Jacobian around equilibrium points for this system. So in general, we can't find the equilibrium points, but if the graph is very specially structured, then we can find at least a large family of them. So circulant graphs have an adjacency matrix with this special diagonal structure. Zero's on the main diagonal, meaning an oscillator is not connected to itself. That's what we always assume. But constant diagonals on the rest of the matrix, notice the symmetry too, B1 on the upper diagonal and B1 on this lower diagonal. What this is saying is, think about one node, think about who that node is connected to around the ring, and then whatever that pattern of connection is, repeat that for every other node as you move around in a circle. So the whole system has circular symmetry, but otherwise it's arbitrary. And so examples of such graphs are simple nearest neighbor cycles. Complete graph has this property. The ones where we connect to all neighbors out to a certain distance on either side has that property. All of these graphs are circulant, and they have the beautiful property, first of all, that these Mexican wave states are equilibrium points for them. And not just the Mexican wave that we looked at earlier, but when you go around the ring, instead of just having one twist in phase, one full 2 pi of color, you could have as many as you want. That's what this number P is measuring. You could have as many twists in the Mexican wave as you want, up to this number n over 2. And what's even better, you can calculate the stability of these twisted states by because their eigenvalues are exactly known. For circulant graphs, you can diagonalize them using the discrete Fourier transform, and you can just write down their eigenvalues. There's an explicit formula for them. So this is what I'm showing on this next page. They have explicitly known eigenvalues given by a certain formula. So I see a number of questions are popping up in the chat. Maybe this is another good place for me to pause. And so let's see what's going on with people in the audience. Okay. Let's see. So Joao asks, is there a model for the syncing of neurons in the brain? Well, certainly there are models of brain rhythms. There are lots of kinds of models. There are models at the extreme simplified end, close to what I'm talking about here with these phase oscillators. Not very realistic, but computationally very manageable. And also you can get some analytical insight like we're trying to do today. And then at the opposite end, there are models that, you know, take into account ion channels in the neurons and try to be very realistic, like Hodgkin-Huxley models or related models. And so those often have to be run on supercomputers. Anyway, absolutely, there's a vast literature about synchronization in brain cells. So you can enjoy looking that stuff up. It's cool. It's a really active area in neuroscience. Let's see, Pedro is wondering, do chimeras play a role in this type of system? So chimeras are states that I'm not going to be discussing today, where part of the system gets into sync and part of it stays disorganized and incoherent. They are impossible, it turns out, in the system I'm considering today. There are no chimera states here because, as I mentioned, the only attractors for this system are not only the only attractors, the only invariant sets really are equilibrium points and stable manifolds of those equilibrium points. So the short answer is no, chimeras are impossible in this system because of the gradient structure. You cannot have chimeras in a gradient system. Let's see, Marcio asks, is it possible to work with Kuramoto equations using difference equations? So in discrete time instead of differential equations. Yes, people have tried doing that. Difference equations are more difficult to analyze and they can have richer behavior. They can show chaos where a differential equation might not have chaos. Like famously, the logistic difference equation has that, the logistic map, even though the logistic differential equation does not have chaos. So yeah, it's sort of similar. If you try to do this with difference equations for Kuramoto, you will get wilder behavior than you would see here. All right, thanks for those questions. I hope some of that cleared things up for folks. So let me keep marching along then. So here we are, we're looking at these twisted states in our circulant graphs, just to show you what they look like. So the one twist, you see, has one cycle of color, and it just rotates around. Here's what two twists look like. Notice I can go, say, from starting here at yellow, I can go around and then I hit yellow again, halfway around the cycle. So there's two full cycles of color. And then that thing rotates around. So that's a state with two twists. You could have four twists, and so on. So you can have different numbers of twists, and that's this parameter P. And then you can analyze and find all the eigenvalues for any P for any circulant matrix. So we now have this vast library of graphs that we can look at. And we did a brute force computer search over all circulant graphs. Remember, what are we trying to do? We're trying to improve that 68% lower bound to try to tighten the vice between the 78 and the 68. We're looking for this, what I called magic number, that determines sort of this threshold above which all we have is global synchrony. So here's the bound from that Ling paper of 2018. They had this bound of 79%. In this picture, here as a function of the size of the network, and here's what I was calling like the candidate for the magic number, the minimum degree over n-1. Everything above this dashed line is guaranteed to globally synchronize. We have a theorem that says that. If you don't insist on a uniform bound, that is a horizontal line, but you allow a line that depends on n, you can get this slightly improved jagged line, the dashed line I'm showing here. And we know that everything above the dashed line globally synchronizes. So there's no hope of finding anything interesting up here. Now, when we look at our circulant graphs like these, and we look for, what is the densest of all the circulant graphs that supports some other pattern, a Mexican wave or something else, these are the densest ones that allow for other structures, the blue dots. And so you see, you can get up pretty high to sort of like around 65, 66%. Here's one that's at 67% dense right there. None of these are beating what I already knew. I already knew 68% examples. So this isn't really helping. It was very disappointing to us, in other words. This is what sometimes happens in research. We just didn't see anything better than what we already knew. We considered more than 3 million graphs here out at n equals 50, looking for something better, and just didn't find it. So, I mean, if you're just sort of struggling to hang on to what is this talk about, I'm looking for a needle in a haystack. I'm looking for some very exceptional graph that is very dense, yet doesn't synchronize. And I'm not finding it just yet. All right, so anyway, here I'm just showing some of these different Mexican wave states for the various examples that we're constructing, but we're not really learning anything new. This approach isn't really giving us new insight. So here's an idea. I mentioned Canale and Monzon. did this beautiful work in 2015. They had a really interesting idea, which was, here's a way to make a graph denser. They called it twinning. What I do is I take, like, let's say here's a case of 5 oscillators with nearest neighbor coupling. It supports this Mexican wave. They said, what if we replace this yellow dot with a pair of yellow dots connected to each other, or maybe 3 yellow dots all connected to each other. And so they, in other words, they replace a single dot with a click, with a complete graph. Here's one with 10. They're all connected to each other. And also these 10 are connected to others in the same way that this yellow was connected to the others. Like here, the yellow is connected to a green on this side and to a red on that side. They take their 10 in the complete graph and connect them to all 10 of these greens and all 10 of these reds. So what's going on here? It's kind of like if you had a microscope. You could think of, those of you interested in neuroscience could think of this in terms of like clusters of neurons. It's like I see a cluster of neurons here in yellow, and when I zoom in with a microscope, I find out it's actually 10 neurons in a complete graph. That's the twinning construction. You take a graph and build up by replacing nodes by complete graphs of a different size. And if you do that, you make the graph denser and denser. But what was so neat about the work that Cornell and Monzon did was they showed that these bigger graphs have the same stability properties as the smaller ones. So if this one was globally synchronizing, then so is this one. Or if this one has some other attractor, then so does this one. And so in this case, it has a Mexican wave attractor and it's stable. I mean, it's an attractor. The same has to be true for all of these, and it is true. So it's a way of making structures that are increasingly dense, yet have the same stability properties. More questions have popped up. Let me look at what those are. What's the role of entropy in these systems, Adriano wonders. How can we define entropy here? I'm not sure how to answer this. I have not really thought about this problem in terms of entropy. So I don't know. I'll leave that to you. There are papers that use entropy-like constructions in the Kuramoto model, but I have not found it helpful myself. So I'll move on. What's the role of the coupling strength on this magic number? Yeah, I don't know that either. We considered this minimal problem where everyone has the same coupling strength, which can be normalized to 1. If you allow different coupling strengths, you have a much wider space of networks to consider. And we don't even understand this problem. So I'm not prepared to answer the harder question that you're asking. What happens if the initial phases are random in a ring graph with just nearest neighbor coupling, what I was calling the cyclic graphs? If you do nearest neighbor coupling, but allow random initial phases, this is a question from Marcus. That's a cool question. We have looked at that. The state that the system evolves to is always a twisted state, but there's a higher probability that you'll go to a state with few twists. The most likely outcome is synchrony, which has 0 twists. There's less probability of going to a state with 1 twist, even less probability of having 2 twists, and so on. You end up getting what looks like a Gaussian distribution of basin sizes. Is there any relation between the eigenvalues and the sync basin? Asks Egon. I don't know that either, although I sort of doubt it, because the eigenvalues are a local issue about local stability, whereas the basin size is a global thing that the eigenvalues don't really control. Let's see, Nasratella asks, which one is better for information transmission, synchronization or phase locking? Usually phase locking would be better. You can actually convey more information through having differences in phases as a meaningful quantity. When you have perfect synchronization, that's a kind of low information state. And so it tends to not be used that often. It's often more in a pathological state like epilepsy. Let's see, Sajad asks, is it possible to use the Kuramoto model to simulate opinion spreading in social systems? People have thought about things like that, where consensus of opinion would be kind of like getting in sync. Although it's a little bit strange because now instead of thinking of opinion on some left-right spectrum, it's like thinking of opinions that live on a circle, which some people say is reasonable if you believe that the far right and the far left are both extremists, and in some ways they're not so different. So there have been some people who have tried to make political models that have Kuramoto flavor to them. I better move along to finish the talk. These questions are taking us in interesting directions. But all right, so let me try to speed up to finish. Okay, so I was mentioning this twinning construction, which was something that's helpful in making ever denser graphs. If we do that, what I'm showing is as I twin examples, I get these curves that monotonically increase. Still, they don't, in terms of going for the magic number, here's the best known upper bound, here's the best we can get with twinning. There's still a substantial gap. This number 6816 improves on what Wiley and Gervin and I found. So Canale and Monzon now held the world record for a while for the lower bound, 15/22. But there's still a substantial gap between the lower bound and the upper bound. With Townsend and Stillman, we did find a slightly more elaborate construction, which was twinning plus adding edges. If you do something like this, you can get just a little bit better than this. So now we hold the world record on this lower bound. It's now 68.28%. But still, it's really frustrating that there's so much space in between, and we don't know what graphs are like in there. Do they globally synchronize or not? And so here's a really tantalizing thing that we found, which was we constructed a sequence of circulant graphs which almost prove that the magic number is 75%. At first, we thought we had proven it, but then we realized it was wrong. In fact, it was one of these people I mentioned, Canale, wrote to us and pointed out an error in our preprint. So it's good to post stuff on the archive because sometimes people will catch a mistake in there before you embarrass yourself and publish it. Here was the mistake we made. We were looking at graphs. We found this interesting construction, like here are some examples of them. They have the property that in the limit, as you make them larger and larger, each node is connected to about 75% of all the others. And they had this wonderful spectrum that all their eigenvalues were either negative, which is what we want for stability, or zero, semi-definite, meaning you either had negative or zero eigenvalues. And the zero eigenvalues are the trouble, because that means that linear analysis doesn't determine the stability. When you have a zero eigenvalue, you have to think about nonlinear terms, and the problem is more difficult. And you don't know if these states are nonlinearly stable or nonlinearly unstable, unless you do some deeper analysis. Well, our computer simulations showed things like this. Here's an example on the left. If I let this run, it looks like it has a perfectly decent Mexican wave, and we ran it for a long time and it looked stable. And so did this one. So we were hopeful that in fact these were nonlinearly weakly stable, and what this would do is give us the hoped for much better new lower bound. You know, you could be 75% connected and still have states that were not pure synchrony as attractors. But that turned out to be false. It turned out these states are weakly unstable. If we made a little perturbation, like of say size 10 to the -6 to this state, it would eventually escape from that state and go to perfect synchrony, but it took 10 to the 6 time steps. In other words, we had states that turned out to be saddles with a very slow leakage, a very slow escape from the saddle along an unstable direction with a zero eigenvalue, but nonlinear terms were taking us out in that unstable direction. So very disappointing, but it came so close to working that we were led to conjecture that the magic number might be 75%, but we just haven't found a proof of that yet, or a graph that will show that. Actually, maybe I should ask the organizers about my time. Is this the time I'm supposed to be stopping?
Yeah.
I mean, I could sort of wrap up. I don't want to go late because I understand that it's always bad to go over time.
Yeah, we have a lot of questions on YouTube. So
maybe it's a good time. Maybe I should pause there then with this, leave this question. We have done further work on the problem. And so we have published a paper about it. You could find it by looking for my name and Townsend and Stillman if you want to read more. But I'd be happy to take the question. So why don't we turn to that then now?
Okay. So I have typed the questions on the chat.
Okay, great. Let's see. Okay. So I guess I'm now at the level of looking at Eduardo's question. Eduardo asks, I don't know if this question is appropriate for a scientific discussion, but do I believe that this is a constant that I'm looking for is some combination of known fundamental constants? Like pi or E or something, or is it some new fundamental constant like Feigenbaum's constant, or maybe something else? Yeah, that's always an interesting question when you're looking for a constant. Maybe I'll stop sharing my screen at this point. I'm not sure I need it. So excuse me, I'm going to go back to looking at everybody. Yeah, so I have no idea. I mean, we think that this constant is actually a rational number. We think it's going to turn out to be 3/4, but who knows? I really haven't, I can't guess. But we do have, like I say, we have tantalizing evidence that there's something special about the number 3/4 in this problem. So I would bet, although not a lot of money, that it's going to turn out to be a nice, simple Pythagorean ratio of small whole numbers. But we'll see. Let's see who's next here. Gab says, I support the political debate for the discussion section. What are other toy model interactions instead of the sign of the phases that the sync community is interested in? Well, another toy model that gets used a lot is what's called an integrate and fire model, which is used very often in neuroscience, where it's a simplified model of a neuron. You imagine that the neuron has a voltage across its membrane that builds up to some level, and when it reaches a critical transmembrane voltage, the neuron fires. So it's like integrating, like a capacitor charging up till it reaches a threshold, then boom, there's a firing. You discharge and go down in voltage and then start building up again. So that's a very simple relaxation oscillator that has some mathematical difficulties because it has discontinuous jumps in it. So it's harder to analyze than the Kuramoto model, but it's a little more realistic in some ways because you can sort of think about a voltage variable. So people look at systems of integrate and fire oscillators. Those are nice toy models. Here's a question. There can be cases where equilibrium points exist in the potential energy surface, but they're not dynamically reachable from generic random initial conditions. Well, let's see. I mean, what we're looking for here are you could think of them as local minima in the potential. They're like little wells that are not the global minimum. They're not the ground state, if you want to speak in the language of physics. So they're not the lowest or necessarily the deepest well, but there could be local minima. And we're looking for those. And so if they exist, they would be reachable. They would have some basin corresponding to all the points in that well. So I think if they exist, they're reachable, but they may have very small basins. It might be very hard to find them. Let's see, Pablo asks, what's the role of topology on the graph? Like thinking about first homology groups or other topological quantities. That's a very interesting question to think about topological aspects of these structures. Also, you could ask a related question about, rather than just networks, we could do multi-graphs or hypergraphs or simplicial complexes, more interesting topological structures than networks that don't just consider pairwise interactions, but consider like interactions among 3 or 4 or more oscillators, little communities. That's a very active area that people are thinking about right now. That's one of the hottest areas, actually, I would say, in complex systems, is to think about more complicated topological issues than you get just from pure network theory. So I don't think I really have time to say much about it, except that it's an exciting area that's really very hot right now. Is synchronization with respect to time? Yes. Is there something like a spatial version of synchronization? Yeah, that would be like crystallization, right? When things get aligned in space, that's some kind of order in space. That's similar to crystallization or long-range order, like you would study in a classical magnetic system or something like that. Yeah, how can I visualize sync with respect to space? I think you should think of particles or objects that have sort of a vector character to them aligning their vectors. So like, say, spin vectors aligning in space would be sort of analogous to phases aligning in time. So there's a lot of analogies between synchronization problems and phase transition problems in classical statistical physics. How do I know that the magic number exists at all? Well, I think almost by definition, it has to exist. There has to be a least upper bound. I mean, I know that there is some number. We already know above 78%. If everyone's connected to at least 78 point whatever percent, there are proofs that it will globally synchronize. So either that's the magic number, or there is some number lower than that with the same property. I think it might be like not a very deep question. I think there has to be some number that with this least upper bound property. Are there some other questions that I missed? Have I hit them all? I think we've got most of them.
There is one more.
Where is it? Sorry, which one is it?
It's in a neuroscientific context. What do you think is more relevant, phase locking or synchronization?
Yes, we did. I think I did talk about that a little bit earlier. Oh, actually, Kevin.
Yeah.
Kevin Liu has a question I didn't get to. This number I'm referring to, a percentage, like 78%, is it a requirement for every node? Yes. Or is it just the average connectivity of all nodes? No. Yeah, it's a very strict requirement. You're asking for the node with the lowest degree, and you're saying that the node of minimum degree is at least whatever, 78% connected or something. So we're not looking at average. It's not a measure of density in the usual sense. You're really looking at the least connected node and ensuring that it has sufficient connection to everyone. And it seems that there is some, like I say, some special number around 75%, but it remains to be seen what that number is.
Okay, then there is the last question from YouTube.
Okay, good.
And therefore we can go to the last discussion. So
all right, let's see. Rodrigo has a question and Elisa has a question. Rodrigo says, thanks for the talk. What needs to be changed or added to observe chaotic attractors in systems like this?